Here's an induction problem 1.3.3. We'll start with n equals 1. And the left-hand side is we start with r equals 1. We'll just plug in 1 here. We have 2 times 1 is 2 minus 1 squared. So that's 1 squared, which is 1. And the right-hand side, we have 1/3 times 1 and 4 times 1 minus 1, which is 1/3 times 3, which is also 1. Step number 2, assume true for n equals k. So this says that the sum finishes at k, some value k, some specific value of k, and we have 2r minus 1 squared, and this should be 1/3 k 4k squared minus 1. So this is what we're assuming to be true. And I always like to put this as our substitution piece. Step number 2 is always your substitution. And step 3, show true for n equals k plus 1. So now what we have here is the sum to k plus 1, r equals 1, of 2r minus 1 squared. This should be 1/3, so we're adding one more term onto this. That should be k plus 1 for k plus 1 squared minus 1. And this, I always like to put next to it, is our goal. And we do not know this to be true. I think it's helpful just to put, this is our goal. We're going to show this is true. We're saying right now it's equal, so I don't want to tell anybody grading my work that I'm actually saying this is equal. It's not equal. That's my goal, to show that it's equal. So let's split this up. So the sum of r equals 1 to k of 2r minus 1 squared plus the k plus 1th term. So the very, very last term in this sum will be 2 k plus 1 minus 1 all squared. So all I did is I just put a k plus 1 into this term right here. Alright, so now we can do our substitution. We see here that this piece here is the same thing I have in step number 2. So I'm going to take this out and I'm going to put this in. I'll just put this green thing here, goes out, and this green piece goes in. So now I have 1/3 k 4k squared minus 1 plus this same thing again, 2k plus 1 minus 1 squared, everything squared. Okay, so now let's start the simplification process. So one of the very first things in induction you should always look to try and do is to do a common denominator. And I can see right here that this first piece is divide 3, so I'm going to do multiply by 3 over 3 on this side, on that second piece. So then I'll have the entire thing is divide 3, and I'll have a k, 4k squared minus 1, plus 3, 2, k plus 1, minus 1, all squared. And now, I'm going to, another good trick is to always try and identify and see when you have a difference of squares. So that's k, 2k minus 1, 2k plus 1, plus 3, and I'm going to simplify this piece a little bit. That's 2k plus 2 minus 1, so that's plus 1, and still squared, all over 3. And you see here, this is 2k plus 1, and this piece has a 2k plus 1, so I'm going to factor out a 2k plus 1. So 2k plus 1 times k, 2k minus 1, plus 3, and I still have another 2k plus 1 here because it was squared. I'll divide 3. And this is just going to be a quadratic, so let's expand that. Two k squared minus k plus 6k, so that's plus 5k. And then we have a plus 3 all over 3. Alright, so let's just remind ourselves what our goal was. I have a 1/3, that's already taken care of. I have a k plus 1, I don't see, and I also have another quadratic that's in vertex form. That vertex form should be a clue that we'll probably be completing the square very soon. So we only have the 1/3 right now. So my guess is this guy is going to factor, and we're going to see a k plus 1 come of that. So let's factor this. We get a 2k and a k. We have 3 and a 1. And they should both be plus. That's 2 and 3 is 5. So yeah, they'll both be plus. And you see our k plus 1. So now I'm going to move that out in front. So I have a k plus 1. And then I have this piece here, 2k plus 1 and a 2k plus 3 over 3. So going back to our goal, we have the 1/3 taken care of, and now the k plus 1 taken care of. And this is a quadratic that's in vertex form. I have a quadratic that's in intercept form, more or less intercept form. We need to convert that into vertex form. So to do that, we're going to multiply it all out, get a quadratic in standard form, and then we'll complete the square and put it in vertex form. It's helpful just to sort of identify where you are and what sort of pieces you're looking like and what forms you need to get them into. Okay, k plus 1. Expand this out, we get 4k squared. 4k squared plus 6k plus 2k is plus 8k plus 3. I'll divide 3. And now I'll come over to the side and do my complete the square piece. So 4k squared plus 2k, make some room, plus 3. So what I do is I take this piece here, 2, and I divide it by 2, which is 1, and then I square it. So 1 squared is 1. Now I just shifted the function up. I can't change the function, I just shift it up. I shifted it up, and now I need to shift it back down. So to do that, I need to figure out how much I shifted it up by. Well, I didn't just shift it up by 1, I shifted it up by 4 times 1. So I need to shift it back down 4. So now it's 4. This is a perfect square. Now that was the whole goal, which means it's k. It's always this divide 2. So k plus 1. And this is minus 1. And there you go. That's now in vertex form. So going back to our problem, we have k plus 1, 4k plus 1 squared minus 1 all over 3, which, as you can now recognize, was our goal the whole time. And lastly, you need to summarize your steps. I'll do this time. I usually don't do this, but because it takes so long to write out on this board, but I'll do it this time. So we have if n equals 1 is true and n equals k plus 1 is true, given n equals k is true, then by the principles of mathematical induction, the statement, whatever's up there, I'm not going to rewrite it, the statement is true for all upside down A, elements, so, sorry, for all n elements of the positive integers that are positive. And that's a statement. Many statements you could write, but I believe that one's acceptable. So there you go.